Hello class, welcome to this video on 10.2 practice part 2. So we're looking at the last two questions, so we're starting at number 3. It says researchers were interested in comparing two methods for estimating tire wear. The first method used the amount of weight lost by a tire. The second method used the amount of wear in the grooves of the tire. A random sample of 16 tires was obtained. Both methods were used to estimate the total distance traveled by each tire. So they're comparing two methods. And they're doing two measurements on the same tire, which means that these are dependent measurements. They depend on the same tire. So they're not. It's not like you're doing independent measurements or anything like that. They're on the same tire, and we're pairing them to get a difference, right? So we know that this has to do with a one sample t-test for mu difference. We're doing a paired t-test here, okay? So and it says 16 tires was obtained, so that means my n difference is equal to 16. And we're looking at just the differences, right? So we're just focusing on that. So 16 of them. And we know that this is less than 30, which means that we need to make a graph as one of the requirements for the test. Okay, so they want us to make a dot plot. So let's go ahead and make a dot plot. And one thing that to note about making this dot plot is that if the dots are too close together, you can start stacking them within if they're within a certain range. Okay, so we're going to talk about that in a second. We got -5, 0, and do 5, and then we got 10. And 15. We're going to go by 5s here. Now, even though I'm going to go by 5s, I'm going to actually tell you what the spacing is between these, okay? So now we got to do the title. So the title is difference. We got weight minus the groove. Now, I know that the highest is around 10, and then the lowest is a negative. So this is why I included some negatives here. But when I'm doing each of these spaces, I'm going to do each of these spaces is 0.5, okay? So that's what these represent. Each of these spaces is 0.5. So when I do that, I should probably be spacing it out more, but that's okay. I'll just deal with what I have here. So we got 0.5, 0.5, another 0.5, another 0.5. 1, 2, 3, and then 4, and then there you go. And so all these dots, so these big ones are obviously those numbers, and then the little ones are 0.5s. This is what I'm going by. All right, so again, each of these dots is 0.5. So now if I have a dot within 0.5, I'm going to stack it on top of the other dot, okay? So there's going to be a couple of these that are so close together, we're going to stack them, all right? And that's because if they're within the scale here, the 0.5 that I'm doing here. Okay, so let's look at the first one. So we have 10.2, all right? So 10.2 is a little bit after this dot, so I'm just going to do a dot right around here. It's sort of like halfway between those two dots. All right, so there's my dot for 10.2, and then we got, let's see, what's the next one? We got 2.7. Okay, so 2.7, it's 1, 2, 2.5, so then 2.7 is right around here. We got 6.4, 6, and then a little bit extra. Okay, so now we got 5.3, which is a little bit after, yeah, so then that means 5.3 is going to be pretty close to 5. Do it there. Okay, and we got 7.0, which is exactly there. Then we got 1.8. We got 1, almost 2. Now here's the next one. The next one is 5.0, which is within 0.5 of 5.3. So since it's within 5 of 5.3, I'm just going to stack them, right? Because it's within the scale that I have. And so that's going to count as a stack of 2 dots. That's what I was trying to say earlier. All right. And then we got 8.6. 8.6. This is 9.5, 9. So 8.6 is going to be around here. All right. And then we got 7.3, which is now close to 7.0. So it's within 0.5. So when I get to 7.3, which is near 7.0, I'm going to stack it. Okay, so I got another stack right there. All right, and then so that's something that, is a subtle difference there. Then we got 3.6. So 3.6, 1, 2, 3. Then we got negative 0.5, which is here. Got 8.4. Okay, now so that was 8.4 versus 8.6, right? So actually I should probably stack that, 8.4 versus 8.6, right? Now for these two, these ones are, I'm going to actually distinguish between what I did here actually, because these two dots are, even though they're less than 0.5 apart, one is on this segment and one is on that segment. So not only is it where you have a segment, right, where this is 0.5, if you have both dots on the same segment, then you could just stack them, right? However, if you have one dot on one segment and one dot on the other one, then it doesn't really make sense to stack them. And that's what I have going on here. In fact, I said I was going to stack them, but I'm actually not, because we got, where is it? We got 8.4, which belongs in the 8.8 to 8.5 stack. And then you got 8.6, which belongs in the 8.5 to 9 stack. Okay, so in that case, we won't group them together. All right, so that's important to keep in mind. All right, so we're just going to leave them alone. We're not going to actually do that. So I just did 8.4, I believe. So let's do 1.0. We got 3.7, 2, this is 2, and then this is 3, 3.5. So yeah, 3.6 and 3.7 belong in the same group because they're within 0.5, and then they're in the same group, 3.5 to 4. All right, so we're going to stack these like that. All right, and then we got 2.2. 1, 2, this is 2.2 over here, and then we got 0.2 just like over here. Okay, so this gives you an idea of the dot plot, and if you never knew about the stacking of the dots, well, now you know. It's similar to like a histogram where you stack them if they're in the same group. So this is the dot plot, and which is a little bit more complex because we have decimal data, but that's okay. So now we're going to describe what the data reveals. So notice that the data reveals that most of the data is positive, right? So most of the data is positive. Okay, so I'm going to say most of the differences about whether the two methods give similar estimates of tire wear on average. Okay, so we see most of the differences are positive. So that means that. So what that means is that whenever we try to estimate by the distance by weight, we get a bigger estimate than if we measure it by groove, right? So that's basically what it's saying, is because we're getting a positive difference, okay? So which indicates that the estimate of distance traveled by using the weight of the tire tended to be greater than those based on the grooves. Okay, so if we use the weight of the tire, the estimate of the distance traveled tends to be greater than when we use the grooves. All right, so part on C, calculate the mean difference and the standard deviation of the difference, and then interpret the mean difference. Okay, all right, so let's go ahead and do that. So the mean difference, we're simply going to add the numbers here, add these numbers up, and then divide by 12. Or I think, how many data points were there? 16 tires, sorry. We got 10. We got 10.2 plus 2.7 plus 6.4 plus ... all the way to 0.2 divided by 16. All right, and then we're going to do this on the calculator. All right, so again, I went ahead and typed the data. So what you want to do is hit stat and then edit, and then you type in the data here into the calculator. And then we go to stat, we go to calculate. We want to calculate one variable stats. List one, and we get our X bar. So our X bar is our mean difference, right? Which is looks like it's going to be if we round it, 4.556. And then our standard deviation, SX, is going to be 3.226. That's what we get. All right, so we're going to go ahead and write the numbers here. So we get X bar difference is 4.556. And then we're going to do the S difference. Now you could do this on a calculator, but I'm going to just demonstrate a few calculations in the numbers. So the formula is you take the difference, the number minus the difference, or the mu difference squared, plus the next number minus the mu squared plus ... all the way to the last number minus mu squared divided by n minus 1. So it's going to be 16 minus 1. Okay. Now this is just to show you the calculation so that you don't forget how to do standard deviation. But you got all this on the calculator anyways. So we get 3.226. All right, so now they want you to interpret the mean difference. Okay, so interpret this guy. All right, so if you want to interpret it, we're just going to say that this is like an estimate. So I'm going to say the estimate of the number of miles driven using weight is 4.556 thousand miles greater on average than estimate based on the groove method. Based on the groove method. Okay, So there's your interpretation. All right, so now we're going to interpret a 99% confidence interval for the true mean difference. Okay, so that's what we're going to do next. Okay, so we're going to do all stages, right? So remember, we're going to do state, all of it. State. So, so what are we trying to do? We're trying to do a 99% confidence interval for mu difference, which is equal to the true difference in the estimate of number of miles driven. Then we're going to do the difference is weight minus grooves. The true difference in the estimate of number of miles driven, weight minus groove, using weight and groove methods. All right, so there's your state, and then we're gonna do the plan. So again, we stated that we're using a one sample, not two, because it's one, we're pairing the difference, right? We're doing pairs. One sample t interval for mu difference. Okay, so there's that. And then we're going to do the conditions. So we got the random condition. So in this case, we got, if you look at here, it says second method, both methods, okay. The table provides two estimates for each tire, all right, and they're comparing the methods, okay. So we're gonna assume random, assume 16 randomly selected tires. Were used. Okay, so we're going to assume that that's the case. And then the 10% condition, we're going to assume that 16 is less than 10% of all, in this case, if we look at the population, it says researchers were, okay, it's a random sample of 16 tires. So this is just tires in general, right? Okay, so less than 10% of all tires, which is safe to assume. And then we have the normal large sample condition. So we got random, 10%, normal large sample. So we got 16, which is less than 30. Okay, which means, let's see, 3 less than 30. And so we're going to need to do the dot plot, okay? So we're going to say the number of differences is small, but now this is where we make the graph. But we already made the graph, right? So if we look at the graph, we can see, okay, the number of differences is small, but there is no strong skewness or outliers based on the data, right? But the dot plot doesn't show any strong skewness or outliers. And then we can proceed with the do. Okay, so now we're gonna do it. So that means we need to calculate the x bar, which we already did that earlier, which is, or the mu difference. Yeah, we calculate the mu difference rather. 4.556. And this is a typo. This should say X bar difference, not mu difference. So I apologize for that. X bar difference, because that's not the mu difference, because we don't know what the mu difference is. So X bar difference is 4.556. And then we got SX is 3.226. All right, so then we can calculate the confidence interval. So it's X bar difference, this is difference, plus or minus T SX. So this should be S difference. I guess we can call it S difference, right? It is SX, but we can call it SX difference or just S difference. Over square root of N difference. So there's your formula for the confidence interval. So we're going to go ahead and do that. So 4.556 plus or minus 3 T star. Now we need to find T star, so let's go ahead and do that. So we're doing a 99% confidence interval. So 1 minus 0.99 divided by 2 is 0.005. And we need our degrees of freedom. So our DF is equal to 16 minus 1, which is 15. So we're going to look up our T star. So our T star, we can do it on the calculator or we can look it up on the table. I'm going to look it up on the table. 15 and then 0.005. All right, so then, okay, 15 and then 0.005 is right here. So it looks like 2.947, okay? 2.947. And we'll show you how to do this on the calculator. All right, guys, so we'll show you how to do this on the calculator. So on the calculator, you want to make sure you hit second vars, and then you're going to want to go to inverse T. And then you want to put in the area, which is 0.005, and then the degree of freedom was, say, 15. And there you go, and you get negative 2.947. So yeah, we on the table we got 2.947, so that makes sense. Okay, so either way, you get the same thing here on 2.947. So now we can plug it in here to this formula times SX or the S difference divided by square root of 15. There you go. We can calculate that. And so what I'm going to do is I showed you the calculation. So now what I'm going to do is I'm going to show you what it would look like on the calculator if you did the confidence interval, right? Okay, so we're going to do a confidence interval. So you're going to hit stat, and then you're going to go to tests. Then we're going to do a one sample t-test. So where is it? Oh yeah, or no, not t-test, interval. I'm sorry. So we're going to go to do interval. So a t interval. So not a two sample t interval, right? We're just doing a t interval, one sample. Because it's technically a one sample. And then we're going to use our data. So I'm going to use data. We know what the statistics are, but we might as well use our data. We got our L1. We're going to use L1 for our data here. Frequency, we're not going to really be concerned with that. We got 0.99 for our confidence interval, so we can go ahead and calculate. All right, we got the X bar. We knew that the X bar was 4.556. We knew that this was 3.226 because we got that earlier. And this is our confidence interval, 2.101, 1801, 6.9324. All right, so then we're going to go ahead and put the answer here. We got 2.1801, 6.9324. All right, so we got ourselves a construction of a confidence interval. Now we're going to interpret the confidence interval. So that is basically we just did the do stage, so now we're going to do the conclude. So we can say we are 99% confident that the interval from 2.1801 to 6.9324 captures the true mean difference, weight minus groove, in estimates of distance traveled. And we wrote it down here, using weight and groove methods. All right, so that's number 3. So let's look at number 4. All right, a bank wonders if omitting the annual credit card fee for customers who charge at least $2,400 in a year will increase the amount charged on its credit cards. The bank makes this offer to an SRS of 200 of its credit card customers. It then compares how much these customers charged this year with the amount that they charged last year. The mean increase in the sample is $332 and the standard deviation is 108. Construct and interpret a 99% confidence interval. And then, okay. All right, so let's do that first. All right, so let's do the state. So what are we doing? Well, we're constructing a 99% confidence interval for mu difference. Now, how do we know it's a mu difference? Well, it says it compares how much these customers charged this year with the amount that they charged last year, right? So you're comparing with the same customers, these customers charged this year versus the last year. So you're pairing the customers, right? Before and after. This year versus last year. Okay? So that's how we know. So the mu difference is the true mean increase, right? In the amount this bank's credit card customers would spend with no annual fee. Okay, so we wanted to see if omitting the annual credit card fee will increase the amount charged. All right, so that's the state. So now we're going to do the plan. Okay, so we're doing a 1 sample t interval for mu difference. Okay, and then we're going to do the conditions, all right? So they said that we had an SRS of 200 customers. So, right, so let's do that. 200 credit card customers. So check on that. 10% condition. We can assume 200 is less than 10% of all credit card customers. And then we got the normal large sample condition. 200 is greater than or equal to 30, which means our sample size is large, right? So that means we're good. Okay. All right. So let's go ahead and we don't have to make a graph, so that's nice. So let's do. Okay, so now, did they give us the X bar difference? It says, yeah, the mean increase in the sample is $332. So the X bar difference is 332. The standard deviation of the difference is 108. Okay, and we need the, we know that the DF is equal to 200 minus 1, or 199, right? And now we can't, well, if we want to be more exact with the t, then we should look it up, right? So I'm going to show you how to look it up. Well, I already showed you how to look it up earlier, so that's using the t inverse function, okay? But if you use the table, then you're going to need to, so we'll compare the table versus the calculator here. So df is 199, the area is 1 minus the confidence level divided by 2, 0.005. So 0.005, we have 199 for the table. So if we go here, the table only goes up to from 80 to 100, right? And then from 100 to 1,000. So if we got 199, we would have to use 100. So 0.005, and then 100 would be 2.626. We're going to now show you with the calculator. So that's 2.626 with the table. I'm just going to put it so I won't forget it. Let's compare it with the calculator. All right, let's compare with the calculator. So we're going to go to second vars, then we're going to go to inverse t, 0.005, that was our area. This one was, well, we don't want to use 100, we want to use the actual one, which is 199. And it's 2.600, so it's pretty, 601 technically. Okay, so that's actually pretty close to that, 2.626, and then, but the actual was 2.601 from the calculator. So we're going to use that, but you can use 2.626, and that'll be fine if you use the table. So this is the calculator. All right, and so let's just show you the calculation. X bar difference plus or minus t star S difference divided by square root of n difference. And so we get 332 plus or minus 2.601. S difference is 108 divided by square root of 200. And of course, we're going to do this on the calculator. Okay, so let's go ahead and do this on the calculator. We're going to do stat. We're going to go to tests. We're going to do a t-test. Now we're going to use stats because we don't have data this time. We know the stats. So we know that. Okay, so here. Oops, I put t-test. I meant to put t-interval. Let me go back. Sorry about that. We want to do. Let's go back to stat. We're going to go to test. Sorry, not t-test, t-interval. I need to go down the t-interval. There you go, t-interval. All right, so we're gonna use stats, and then we're gonna type in the stats that we got. So the X bar, I gotta look it up. I forgot what it was. We calculated, or they gave it to us, I think. Yeah, so they gave us, it was $332, and then the standard deviation was 108. Okay, and we had 200 customers and 0.99. All right, so it looks like we get our confidence interval, 312.14, 351.86. Okay, so let me put that here. All right, so there you go. So now we're going to conclude. We are 99% confident that the interval from $312.41 to $351.86 captures the true mean increase in amount this bank's credit card customers would spend with no annual fee. All right, so there you go. So that's part A. Now, part B, it says, based on the interval from part A, can you conclude that dropping the annual fee would cause an increase in the average amount spent by this bank's credit card customers? Why or why not? Now, it says, can you conclude that dropping the annual fee would cause, okay, an increase? So remember, how can we conclude cause and effect? We can conclude cause and effect. This is a Chapter 4 question, by the way. Chapter 4, Unit 3, Chapter 4. So you can conclude cause and effect if you have random assignment, right? So did we have, or and you know, all that stuff, right? So that we have random assignment and all this stuff, but also we would need a control group to be able to compare, to be able to effectively compare this and then randomly assign them, right? So a treatment. Oh, actually, this wouldn't make sense in this case because I forgot. That's the same customer. So you're looking at the same customers before and after, right? So last year versus this year, and then they omit the annual fee. But then you would have to compare these results in that case to a control group, right? So in this case, the control group would be what would the difference look like if they didn't offer them at all, right? So if they didn't offer in this case, the omission of the annual credit card fee, okay? And so we won't be able to compare it unless we know, what happens without the annual fee, okay? So the answer is no, as we would need to compare the result to a control group in which annual fee was included. And comparing the differences. Okay, all right, that's going to do it for the video, guys. Hope you found this useful and informative, and as usual, I'll see you in the next one.